All right, good afternoon, everyone. We hope you all are staying safe and healthy, and thank you for joining us today for our webinar on understanding fluctuations and equilibrations. Let's see. So today's webinar is funded through a grant by the National Endowment for the Humanities. So we'd like to thank them for their continued support. This is the start of our second series, which is designed for institutions with a year or more's worth of data, when you're really ready to start evaluating your spaces and determining those next steps forward. If this doesn't describe you or doesn't describe you yet, we would encourage you to check out Series 1, which is recorded and available on the IPI sustainability page, the same location where you would have found information on this webinar series. If you are registered for this webinar and attending it live, you are automatically registered for the next two in this series, which are going to be taking place on June 11th and July 9th at the same time, 2 p.m. Eastern. So please join us for those as well. If you're unable to make those dates, those webinars, as well as this one, are being recorded and will remain available for at least a year on that same IPI sustainability page. So please ask questions as they come up, which you can do by typing in the chat box that you see on your screen. Chris will be helping to address any questions that come up in the course of the webinar, and then sending those along to myself, Jean-Louis, and Al at the end to answer any remaining ones. So appreciate any questions you have. If you're watching this as a recording or you have a specific question or something comes up later, you're also welcome to email us directly at any point. So just a brief introduction to IPI for those of you who may not be familiar with the lab yet, but IPI started in 1985 studying film and photographic materials. And kind of seeing the importance of environmental conditions on their preservation expanded its scope to address this concern for more materials. So presenters today, myself, I'm Kelly Krish. I'm the Preventive Conservation Specialist at IPI. I trained as an art conservator and came to IPI 4 years ago to work on the environmental consulting team. So I work with Chris and we go to museums, libraries, and archives across the country to help them improve the preservation of their environments, as well as to do so in a sustainable and energy efficient way. Joining me remotely are Jean-Louis and Al, two of our research scientists at IPI, and you'll see their work over the years referenced multiple times throughout this webinar. So if you have any specific questions, we're very lucky to have them with us as well, so they can address those questions. So considering the topic, I just wanted to first off start off by just these two caveats. And one is that, in the course of a 45-minute webinar, we're going to try to give you the broad sweep of our understanding of fluctuations and equilibrations as it stands now. So unfortunately, that means that we can't necessarily talk about the specifics of every possible collection material that you might have in your collection. And so really we wanted to empower you all. This is the information that we have available, and we're happy to answer any questions, but really it comes down to the collections professionals to take that information and apply it in the most meaningful way for their specific context. Specifically, going through kind of a risk assessment process and understanding what each range of conditions might mean for their collections. And the other factor I just wanted to mention is that this is very much a field of ongoing and active research, specifically with environmental research. So we encourage you to stay tuned, and this will be kind of an evolving picture of the environment for collections, and may not be the last word. So please stay tuned as we complete more research on this topic. So I just wanted to kind of start off so we're all on the same page. You signed up for the webinar, so you probably have a sense of what these terms mean. But just so we start off with this, an equilibration essentially means that that object has reached a state of balance with its environment. So as long as those conditions are maintained, the object itself is not going to be responding any further. whereas a fluctuation, which is what you see in the graph to the right, is really any change from a previous measurement. So this could be, a single event, like we see all those individual peaks and dips, or it could be part of a larger trend. And right there in the middle of the graph, you kind of see how it's repeated fluctuations, but an upward trend. So fluctuation, that term kind of encompasses both of those examples. So why would fluctuations occur? There's a number of reasons. These are just some of the main reasons why. When we talk about mechanical systems, it could be a result of typical operation. A lot of systems, it's difficult to control in a completely flat line, so there's just natural variation in the conditions that are provided to a space. This can be further exaggerated by any system malfunctions or disruptions, as well as intentional changes. And this could even be done for sustainability purposes. And we'll talk a little bit more about that at the conclusion of the webinar, but if you're interested in implementing seasonal set points or other strategies to improve your sustainability, you could also see these fluctuations occurring in your collection spaces. There's also, aside from the mechanical system, there's environmental loads on the spaces that can result in fluctuations. You can see in this photo here, we have a collection object next to a window. There's quite a bit of light coming in there, and with that, a lot of heat from the sun. So in this case, if we had a logger next to this object, we'd likely see some fluctuations in, as the temperature increases throughout the day and then drops at night. And finally, there's the movement of the objects themselves, whether that is, loans from one institution to another in a different climate zone, or it's within the institution itself when we retrieve objects from cold storage or just from a cooler storage space and bring them out for researchers or exhibition. And there's also treatments. A classic example of this is pest eradication, where we often use low temperatures to try to eradicate pests and protect our objects when they come into collections. So when we talk about fluctuations and equilibrations, there's a number of things that can make us concerned. Sudden changes, if you see sharp peaks or drops in data, can be alarming for collections professionals, as well as slow changes. If you realize that dew point has just slowly drifted up every summer. The extent of fluctuations, if you see them, all of a sudden you go from 60 degrees on up to 80 degrees, that can be cause for concern. Or repeated fluctuations, when you just see it, constantly cycling between within a certain range, maybe between 30 and 50% RH, but it's doing it, over, every couple of days for weeks on end. Those are things that we have concerns about. And so the goal of this webinar is to kind of address each one and talk about when it's a concern, when it might be less of one, so that we can really focus our efforts on mitigating the issues that really pose the biggest risks for collections. And so the reason that we're concerned about these things is because we don't want to see damage caused in these three ways. These are the three ways that environments can cause damage to collection objects. So this chemical decay, again, is, as we usually relate it to temperature, but it's those chemical reactions that are occurring, the natural aging process. And as we see higher temperatures, those reactions occur faster, and so decay happens faster. Mechanical damage tends to be when we see those objects physically expanding and contracting, and we get the cracking and other forms of damage like you see on the spine of this book here. And biological decay, we want to avoid mold and mold germination and pest activity, from manifesting themselves in our collections. So if we have these concerns, why don't we just maintain conditions, or what people would typically refer to as flatlining? And there's a number of reasons why we don't want to do this. And for one thing, unless you have a purpose-built storage environment, with vapor barriers and insulation and everything, we can definitely cause damage to structures. In the background of this photo, in the background of the slide, you'll see a photo of a collection storage space. It's a brick wall, and you can see that throughout the year, they're driving moisture in and out of that brick envelope in response to the different conditions between the inside and the outside of that building. And so you can start to see, forms of damage coming onto that wall. If you have a historic structure, that's obviously the largest object in your collection, and so we definitely want to preserve those as well. And of course, the greater the difference between the inside and the outside environments, the greater the potential for damage. It also does not necessarily maximize the preservation of collections. If we have an opportunity to achieve a lower relative humidity or lower temperatures and then therefore increase the preservation, we want to do that rather than prioritizing maintaining a flatline condition. So we really want to take advantage of preservation opportunities when we have them. And additionally, it's not always practical. We mentioned before, but it is very difficult for mechanical systems to turn out a constant flatline condition. And for those of you who may be able to do so, it's even more difficult to do that without incurring considerable expense and certainly a lack of sustainability. So as those outside conditions change, again, and we're still trying to provide the same conditions inside, we're having to do increasingly more work on that air in order to provide those conditions. So these are just two studies that I wanted to include to kind of illustrate this point. It's not to say that this information would necessarily be directly applicable to everyone's scenario, that if you institute the same changes, you'll see the same cost savings, but just meant to give you a sense that we're not, this isn't a small decision in terms of effects on the cost savings. So as we broaden those conditions, and in none of these instances are we recommending that you sacrifice preservation or that you put the collection at risk. We're just implementing the correct band for the collection. They did result in energy savings, and you can see specifically in the case of the National Archives where they were measuring this, that actually did ultimately result in an increase in preservation as well. So if the goal is not to maintain flatline conditions, but it's still to avoid these risks, how would we define what we want to do in terms of fluctuations? And the way that we define optimal is we want to achieve the best possible preservation of the collections with the least possible consumption of energy. And so you'll see that throughout this PowerPoint, that's our goal in terms of understanding what represents risk and what situations are really within the realm of good preservation. So I'd like to start by talking about temperature, and we'll talk about the different types of fluctuations with temperature, and then we'll move into relative humidity. So the data shown here is actually fairly representative of most collection materials. And the main takeaway is that temperature equilibration is pretty fast, that it's usually no more than 4 to 6 hours for almost 90% equilibration. So it tends to be a fast process. This is data from an experiment that Jean-Louis did, and it represents 3 one-time temperature transitions for a stack of 1,000 prints in a cardboard box. And his goal in this experiment was to see if it mattered which direction the temperature change was occurring. So for example, did it occur slower if we were going from a high temperature to a lower one, or vice versa? And then also, did the extent of the change matter? So does it matter if it's a 10-degree temperature change versus a 20-degree change? And you can see from the data on the right that in fact, the extent and the direction did not matter. That equilibration is really determined by the set gradient, and so it takes about the same amount of time no matter which direction or how big the change is. You may see some change in the rate of equilibration depending on the thermal mass of an object or how much exposed surface area it has, but the main takeaway from this data is that equilibration is fast. Moving on to, okay, so what if we see this sharp rise in temperature? And usually when we see this, we're concerned because it means that we're going to have accelerated rates of chemical decay. So certainly an abrupt rise in temperature is cause for concern because we want to minimize that time spent at high temperatures. Now, vice versa, if we see an abrupt drop in temperature, usually the concerns we have regard, freeze-thaw process, dehydration, condensation occurring, or even swelling. And the studies that have been done that look at this have found that most objects really lack sufficient moisture for these to be issues. And when we follow the procedures outlined for either low temperature pest treatments or for implementing cold storage, what we really see, using bagging and the appropriate wait times and preconditioning, that we're able to avoid those risks. So usually the drop in temperature is not a cause for concern, certainly not as much as that rise in temperature. Okay, so moving on to the extent of fluctuations. I think for a lot of people, if you see the graph at the left is probably a little bit more concerning than the graph at the right, where you see the, a much larger range of fluctuations as compared to that graph on the right. But most studies have found that temperature fluctuations really are less of a concern than we might feel. The Canadian Conservation Institute, for example, has found that many objects are far less sensitive than what we're basing the standards on. And so, daily fluctuations of 20 degrees Celsius or even 40 have really, really haven't caused any additional harm to objects. The main key with this is that we still want to avoid extremes, and we certainly want to avoid those high temperatures. So it's not so much the extent of the fluctuation as what that fluctuation is taking you up to, the temperature that you're rising up to. Now, the caveats for whether an extent of fluctuation can be concerning, there are a couple, and one is the coefficient of thermal expansion. And a good example of this is particularly for plastics collections. And so the coefficient of thermal expansion describes how the size of an object changes with the change in temperature. So if you have a material that is particularly responsive to changes in temperature, that can cause some issues if you have a broad fluctuation. The other issue is gradients. This tends to be a bigger concern for particularly thick-walled objects, and that results in a temperature difference between the core and the periphery of the object. Again, the Canadian Conservation Institute, they generally recommend that those temperature differences be kept below 10 degrees Celsius. And so this really isn't often a problem because we talked about how quickly those objects are equilibrating almost completely to temperature changes. So to get that big of a difference from the surface to the core of an object is perhaps an unusual circumstance. And there can be some softening of components. Again, this comes at if you have a fluctuation that goes to a higher temperature. So overall, again, those concerns are with those higher temperatures, and it's still better to achieve those lower temperatures and slow chemical decay when you can than to maintain those flatline conditions. Okay, and then the final scenario for temperature is the effects of cycling. So when we see it kind of bouncing back and forth between different set points, is this a concern? And one of the studies I'd like to cite was a paper done by Ellen Carley on does low temperature pest management cause damage? And in it, she discusses experiments with wood and textiles and insects, a wide variety of materials, and really there's been no significant structural damage occurring with repeated freezing cycles. Even insect specimens, which are considered fairly vulnerable to this, were cycled from freezing to room temperature for 2 cycles every 18 months. And not only could they not observe any damage to the pigments or structure, but they couldn't even see any microfractures under scanning electron microscopy, so under very close examination. Multiple studies in other sources have also confirmed this, that there really doesn't seem to be any additional adverse effects from materials. One question that still exists in the literature is concern over thermal fatigue. So this is the idea that each time you go through this process, are you kind of building up an accumulation of strain that will, over time eventually cause damage. There's not a lot of data to address that question. But I would again go back to the fact that of the studies that have looked at cycling, so far we are just not seeing that additional adverse effects. And I wanted to share with you some data from one of those experiments. So this is another one that Jean-Louis did on acetate base. And so you can see here, this was taking that acetate between 20 degrees Celsius and 50 degrees Celsius over a period of 6 months. So if you go between 20 and 50 degrees every day for 6 months, you get 180 cycles, which is that blue line there. If you take 3 months to go between 20 and 50, you can of course only fit in 2 cycles. So that's the green line. And what this data is really showing us is that results can be explained by current theories. There is deterioration present, but there's no extra chemical decay from that cycling. It's all explained by the amount of time spent at each temperature. And so the main way that we can understand the effects of temperature fluctuations is through metrics like the time-weighted preservation index. This is one example. There are other models. They all tend to be pretty much in agreement for how temperature affects preservation. And the general idea behind this is that temperature is not linear. It's that time spent at each temperature. I think the best analogy is really if you think of a carton of milk, if you leave it in a fridge, maybe it lasts 2 weeks. And if you leave it out on the counter, let's say it only lasts for a day. Well, that's very quick, but just for the purposes of simple math. And then, but if you take that carton of milk and you put it in the fridge for a day, and then you put it on the counter for a day, and you put it back in the fridge for a day, it's not going to last exactly 1 week, halfway between those two. It's actually going to be shorter than a week because that time spent at bad conditions counted for more. We didn't reverse any of the deterioration, we just slowed it. So hopefully that makes sense. If you have any more questions about TWPI, we do have additional materials kind of explaining how that works. But this is one way that we can kind of account for how fluctuations can impact preservation. But just remember that brief changes in temperature aren't going to cause the collection much damage. Chemical decay is a slow process, but it's those sustained warm temperatures that are the issue. Okay, so when is temperature a concern? And we talked about it really, if it's outside the safe range for objects, especially high temperatures, that is a cause for concern, and it's something that we would want to address in the short term rather than long. And the other two situations are if the temperature causes the relative humidity to be outside of the safe range for the objects. So generally what we see is that temperature and relative humidity have somewhat of an inverse relationship. So if we lower the temperature, we tend to see the relative humidity go up, and vice versa. And this is an issue because it can, if we have relative humidity that's climbing, then we put our collection at risk for other forms of damage, such as mold germination, mechanical decay, metal corrosion, and pest damage. And the other issue is if it's uneven across the space. If you have temperature variations within a room, it's difficult to manage because you get the creation of these microclimates. And for the same reason that we were concerned about relative humidity, again, we're concerned about microclimates because then we get these pockets that have higher relative humidities and put us at risk for those types of damage. So a lot of the reasons for concerns over temperatures have to do with its effect on relative humidity. And again, this main takeaway, it's the sustained high temperatures. So it's not brief fluctuations or fluctuations within, a safe range. It's the sustained high ones that are going to have the most impact on the preservation of collections. Okay, we're going to move into moisture equilibrations. Hopefully that all made sense. And again, if you have any questions, feel free to send them Chris's way, and we'll be sure to address those. Okay, so for moisture equilibration, it's different than temperature equilibration. Material changes, responses to changes in relative humidity really occur pretty slowly in compared to changes in temperature. If you have a single sheet, it can maybe reach equilibration within 2 to 12 hours in a moderate relative humidity change. But really, for most collections in typical storage configurations, we're really talking about a month or so, or plus or minus, to really achieve equilibration. And that's different than what we saw for thermal. That was really just a matter of hours. And the process is just really more complex. There's a greater variation in the capacity of individual objects to control moisture equilibration. And additionally, at an object level, we often have major differences between the surface of an object and its core. And again, we're seeing those slower rates, so you have a greater potential for gradients throughout an object. It's controlled by this diffusion rate, and so it just goes slower. Additionally, lower temperatures are also going to slow that diffusion, and we've really seen that response times at least double for every drop in 18 degrees Fahrenheit. So if you're taking an object from an exhibit and putting it back into cold storage, it's going to take much longer to reach moisture equilibration in the cold storage than it took in the exhibit space. So hopefully the video works. And I just wanted to take a step back and just kind of explain again what we're concerned about with moisture equilibration. And hygroscopic materials, which is materials that are going to respond to changes in moisture content. As you can see in this time-lapse video, they're kind of expanding and contracting as they absorb and release moisture. And that's it's a little difficult to see, but the relative humidity of their environment is changing, so they are also absorbing and releasing moisture in response to that, and you start to see this curling and deformation on the surface. Other types of damage that we relate to this are flaking, cracking, and possible loss of any inks or colorants that might be on the surface. So this is, I think, pretty new data from Jean-Louis, and here you can see how the response of a variety of different paper-based materials. And really, this is, so we're not so concerned about the relative humidity of the environment as a whole. What we're really concerned about is the moisture content in the objects. So the reason we're concerned about relative humidity is because of its effect on the moisture content, which is really the amount of water in an object after it's reached equilibrium. So you can see in this graph that the starting point kind of varies by material. It can vary based on the history of the object, whether it's historic or more modern, but generally that moisture content is increasing with every increase in relative humidity. And the reason we're concerned about moisture content is because that results in a physical change that can cause strain and stress as they expand and contract. And so this is a video from an experiment that Al performed, and this is showing a vellum-bound book responding to changes in relative humidity. It might be a little difficult to see, but there's a data logger in the background showing those changes. And the color changes you're seeing represent the amount of strain experienced by each part of the spine of the book. And so when we see the red color, I'm just going to go ahead and replay that. The warmer colors represent the greatest amount of strain, where like right there, whereas the cooler colors represent less strain. This becomes an issue because you can see for the most part, the book responds to a change and then it goes back to its original position. And so this is elastic. It's just like a rubber band. You can stretch it and it returns. And so we're within that elastic range. But our concern is that we don't want to go beyond this critical point and cause irreversible damage. You don't want to stretch that rubber band past the point where it can return to its original spot. When we do this, we are causing plastic deformation, and that's non-reversible. So again, the goal, the concern is that relative humidity causes those changes in moisture content. That moisture content causes physical changes that result in strain and stress. This graph I included to show, this is also from Al's experiment, but this is to kind of illustrate in a graph form rather than visually. But you can see this relationship between the relative humidity and the strain, that as the relative humidity increases, that strain is as well. And here, this is some data comparing papers with vellum, and the main point here is also that the strain is material dependent. So not all objects will respond in the same way. We saw they had different starting points, and they're going to take on different amounts of strain in response to changes to moisture content. All right, so let's apply that to some data analysis. When we see a rise in relative humidity, should we be concerned? And we often are, because we relate high relative humidity to accelerated biological decay, mechanical damage, chemical decay, all three of the main categories. And the good news is good and bad. The good news is that the relative humidity, again, it has to be sustained for the objects to heal. Even mold growth, you can see a plot of mold germination below the relative humidity graph there. And you can see it's not an isolated spike that's causing the mold germination. It takes time, and it takes sustained high levels of relative humidity for mold to germinate. So that's the good news. However, we wouldn't want to maintain high levels of relative humidity, because we really do want to avoid those risks as much as possible. When we see a drop in relative humidity, often our concerns are over cracking, shrinkage, delamination, and the extent to which this is a concern really depends on the history of the object, its specific context. And to talk more about that, I really want to get at the concept of proofing. And this is really an idea that if an object has experienced a similar environment in the past, putting it back in that same environment won't cause significant physical damage. So again, this only applies to physical damage. If you have an object that's experienced high relative humidity levels and had mold germination, putting it back in high relative humidity levels, it will probably again experience mold germination. So it only applies to physical damage, and it has to account for the current condition of the object. So if something has been treated, that kind of resets its state and damage can be caused again. So I think perhaps this is best illustrated by comparing these two graphs. These are the dew points for Helena, Montana and New Orleans, Louisiana. And if dew point doesn't sound familiar to you, I would certainly encourage you to check out the webinars in series 1, where we go a little bit more into that. But you can see here, Montana obviously has a much drier climate than Louisiana, so the objects that are in Montana have experienced more consistent lows than those in Louisiana. And when we take, so the amount of risk that something like 60% relative humidity might pose for an object is very different if they're coming from these different climates. In Montana, they may never have experienced that. And so when they go to expand, they could very easily crack to try to take on that additional moisture. Whereas in Louisiana, they probably have experienced 60% relative humidity. And so any cracking that was going to form from that expansion has already done so. I should just say too, the nice part about proofing is that essentially just by avoiding previous extremes and making moderate changes to the control of our environment, we can really avoid that risk of mechanical damage. So if an object has a history of going from 20 to 60% relative humidity, the concern isn't that we need to flatline at 50% for the rest of its life. We know that by staying within that range, that we shouldn't see any additional mechanical damage. Okay, so moving on to the rate of change. Again, this is it's a slow equilibration, and the material is regulating the rate. It's controlled by diffusion. So it seems likely, from our understanding currently, is that the rate of change is not a factor. The main thing that matters is that it's kept within the allowable range. I'll talk a little bit more about an allowable range, but for the purposes of right now, consider 30 to 60% relative humidity is about what we're talking about. So it's really that staying within the range is the most critical part. There are some areas of research that, or some questions that need some further research as well. For example, there's competing studies that argue over, one would say that, for stress relaxation, if you apply the change more slowly, the material can handle it better. But other studies have shown that by applying a slow change, you're allowing the object to change at a molecular level, and so that change is more likely to become permanent. So there's still some questions about the rate of change that we don't fully understand, but currently the best understanding, the best advice from all of the studies is really that as long as we keep it within that allowable range, the rate should not matter. This graph is meant to illustrate that, when we do see seasonal cycles in relative humidity, the objects are feeling that. So even though they might not feel those short terms, those longer term trends are definitely being felt by the objects. So that's where we want to focus our efforts on. Okay, in terms of the extent of the fluctuations, really, consistently, most studies have found that objects can actually tolerate much larger fluctuations than what was originally thought. So plus or minus 10%, even 15% is really okay. Again, the main thing is that we need to stay within that safe range and avoid extreme conditions. This is a little complicated if we have any objects that are restrained or this coefficient of expansion idea. So in particular, if you think of composite objects, so those that might have more than one material and are joined together. So if an object or a component is restrained by another component that might be expanding and contracting at a different rate, you can see where that might cause some friction and result in damage. And also coefficients of expansion also come up when we talk about those internal gradients and how there could be a difference in moisture content from the surface to the core of the object. Okay, so these are moisture isotherms. We actually looked at these earlier in the webinar when we were looking at, again, it's the graph of the moisture content in response to those changes in relative humidity. And the reason I've included here is this is really to show you where we came up with that, that range of 30 to 60% relative humidity. So the reason is that the moisture isotherms show the flattest areas in that range, in the 30 to 60 range. And so that means that when we change the relative humidity within 30 to 60%, we're seeing the least amount of change in moisture content. So that means the least amount of physical change and the least amount of change in strain, as long as we're staying within that range. And you can see, so the graphs on the left are taken from a study that was comparing modern and historic parchments, and the graph on the right is composite. It's a painting, and so it's showing how just the different composite materials are responding. And you can see again, while they do deviate outside of that range, within that 30 to 60%, you're seeing pretty small changes in moisture content for all of those materials. And multiple studies have kind of shown that for a wide range of materials, it's similar results. Okay, so the effects of cycling, if you see your relative humidity going up and down and up and down, is this a concern? As long as it's kept within that elastic range, they really have found that there's no structural effects on objects. The only exception that I found for that was really there's a concern over creep mechanisms, and that really came out of a study done on historic tapestries. So because they're hanging on their own weight, as they absorb moisture, that adds weight and they pull down. So then again, if they release and then more moisture is added in and more weight, they might pull a little bit more. So if you happen to be in that circumstance, that might be something to consider. But for most objects, that's not something that, usually they're not expected to bear the weight of their own loads. So the main takeaways here, again, relative humidity is a risk if it's outside that safe range for objects. If it's more than 30 to 60 for the most part, we might shift to that range slightly depending on, where we are in the country, as we saw in comparison to Montana and Louisiana, and also if it's uneven across the space and we have potential for microclimates. But overall, again, it's those periods of sustained levels of humidity and particularly high humidity that are most significant for preservation. So we talked about before how, in terms of how this applies to collections and taking into account the specifics of everyone's situation. And so that would be done through a process of risk assessment. There are a lot of other resources that get in more detail about risk assessment. So I just wanted to touch on some of the factors that make objects particularly vulnerable to fluctuations. And so we'll look at starting with the object itself. These are some of the factors that may make an object more vulnerable to them. So if you see these types of things within your collection space, you might give extra concern to this, and you might want to consider either, we'll look at enclosures and other levels of control that you can implement to try to mitigate the effects if these are concerns for you. So in terms of composites, you can see the object on the left is a table and has a laminate surface. So it's just a really thin layer, and it's responding differently than the bulk of the object. And so we're seeing that kind of buckling in the middle that was caused from its quicker response than the rest of the object. You can also see on the right, this is something that's restrained. So this block of wood in a chair has been restrained by the other pieces of wood as well as those nails, and so cracks have formed because it's tried to shrink and expand into areas that it can't. And so there are another number of other factors as well that can result in an object being more vulnerable. Next, this was in terms of exposure and how we might control it. When we talked at the beginning of this presentation about the reasons why fluctuations occur, so there are a number of things, whether it's the mechanical system or things coming in through the building envelope or just the movement of the object itself. So if we're concerned about fluctuations, we can deal with these in a variety of ways. And we want to find the one that is most cost effective and sustainable, makes the most sense for addressing our particular concerns. So I just want to talk specifically about enclosures here. And this is some data from an experiment that Jean-Louis did. And you can see that for most enclosures, and we see this as well at institutions with exhibit cases and everything, usually we see very little difference in terms of thermal equilibration. So this graph shows you, within these cases, they're pretty much responding to the full extent and pretty rapidly to any changes within the environment itself. However, when we look at moisture equilibration, it's a different story. And we often see that enclosures can slow and reduce the effects of relative humidity changes. So we always encourage people, if they are concerned about changes to relative humidity, to make sure that the data you're collecting is where the objects actually are. If all of your materials are housed in archival boxes, be sure to put a data logger within the archival box itself, because it may show you that those materials aren't seeing those the high fluctuations that are concerning you, and the environment within the box where the collection objects are might still be within a safe range. So this was an experiment that looked at the same types of enclosures and did a one-time change from 20% relative humidity to 50% relative humidity. And you can see that at least in the case of two of the boxes, they did a good job of slowing that moisture equilibration. And here it is, if the blue represents changes to the environment as a whole, so the room or the space, if you saw this kind of increase in relative humidity, would it make a difference? And you can see that in all of these cases, by the time they reach that full peak in relative humidity, it's delayed by almost a month from when the room itself felt those conditions. So it is delayed. And additionally, you can see that, for example, the portfolio box, it never got up to that full extent. So all of that is good news in terms of the effect enclosures can have in helping to address some of our concerns about relative humidity fluctuations. It's also good to think that, thinner objects are usually the ones that are responding the most quickly, but they also tend to be the ones that we can put in enclosures and that can benefit the most from these. So that's a nice a nice match there. So next, I wanted to talk about the data that I'll show on this and the next slide come from experiments done on a contained or a sealed space. But what they're illustrating here is that if you have an empty space, which is illustrated by the darker red line, and it has these changes in temperature and relative humidity, versus if you have a space that's full of hygroscopic materials. So if you have a high density storage space, you have archival records, floor to ceiling, yes, they might respond to those changes in temperature, but that lighter red also shows that those changes in relative humidity are not felt at all. That is almost flatline conditions. So the materials are able to kind of buffer all of those changes. And of course, the more hygroscopic materials we have, the higher density we have, the smaller the relative humidity fluctuations are. So I just wanted to do a quick plug as well for other methods of trying to implement and manage fluctuations. We have this book is available for download for free on the IPI website that's listed there. So it's methodology for implementing energy saving strategies. Seasonal set points is one example that you saw throughout this presentation, where you can change the temperature and relative humidity goals across the seasons to kind of take advantage of better preservation and reduce the amount of work the mechanical system has to do. So not only can we manage it at an enclosure level, we can also manage it within the mechanical system itself. So main conclusions, again, don't sweat the small stuff. Short-term relative humidity fluctuations aren't fully experienced by the collection objects, and short-term temperature fluctuations don't last long enough to cause chemical deterioration. So it's really those longer term changes that are what we're really concerned about. But fluctuations do happen, and sometimes even for good reasons, and that's all okay, as long as we focus on this kind of risk assessment based approach that allows us to optimize the environment. And again, I just wanted to mention there's ongoing research. We have another research project concluding at the end of the year, so please do stay tuned for that. And finally, I want to thank you all for attending, and please do consider taking the time to complete the post-webinar survey. It is brief, and we really do pay attention to your feedback. The information gathered helps us to evaluate our approach in this grant, strengthen our educational resources in the future, and to report back to NEH on the project. So please do consider filling that out. Thank you all, and I think we're going to open up the talks to Al and Jean-Louis as well. So if anyone has questions, Chris will be voicing those now.
All right, Kelly, I have a couple questions. We'll go in order of what we received. We'll start with one question that came in for Jean-Louis. Does cycling add to the expense of running the equipment?
Well, this is it's a really strange question. I'm not sure if I understand. There is a lot of, as you know, Chris and Kelly, of course, a lot of sustainable strategy that will create cycling, right? And if you apply this type of intentional changes, actually you save energy. So the goal is not to, I think, to implement necessary cycling as a strategy. So that I'm not sure about the question, what he meant there, or she meant. Does it make sense to you, or do you have a different reading of this question? Yep.
Chris, I was gonna let you answer that.
That makes sense to me. I was looking at some of the other questions we had coming in at the time.
Okay.
I'll pass the next one to Al. Al, what is the technique used to demonstrate the strain in the vellum book, the vellum bound book? Sorry.
Yeah, sure. So the technique is called digital image correlation, or DIC, and it's a photogrammetry technique. It uses 1 or 2 cameras, in our case 2 cameras, set up in stereo. If you remember, you saw the object was covered in little black dots. And so as the object expands and contracts, we're taking images at regular intervals. And then those images are uploaded into a software which actually tracks the movement of those dots and measures the extent of change, the extent of expansion and contraction, which then gives us data on strain, as well as kind of extent of expansion and contraction. We can do videos like this. We can do 2D and 3D models. So yeah, it's a really interesting technique, and it's been adopted recently in cultural heritage preservation or research fields for paintings, as well as the tapestry project that Kelly had mentioned used DIC. So yeah, it's a pretty interesting technique. It only gives strain though. In terms of if we're talking about the different kinds of data, it does have some limitations.
All right. The next question we have, I'll pass over to Kelly. May we have some reference for the proofing hypothesis?
Sure. I'm trying to think if I can, I don't know if I can include that on the website as well, but it has to do with, and Al, you can expand on this as well, but it has to do with studies that were done by Mary Mecklenburg at the Smithsonian, and there were numerous papers published on it. And is that that's correct, Al? Right? Or
honestly, I don't remember who did the study. If it was if the paper was McCormick Goodhart or Mikulski, but go ahead.
yeah, I think you're right. I think it, I'm sorry, I misspoke. Not my site. I have another citation from Mecklenburg here, but I believe you're right. I think it is Mikulski and Goodhart. So I will locate this now, and I will put it in the chat box for everyone.
All right. The next question I'll give to the entire panel. Should there be a wait period when removing a vellum book from the archival storage to a reading room, especially if the leaves are to be turned by a researcher not familiar with vellum?
Okay, I give a crack at this. So I mean, we know by listening this talk that basically what determines the physical property of hygroscopic material, it's moisture content, right? The problem with a book like the one which is, by the way, on the video, it's very complex structure, and the vellum. Why the cover is flapping like this is because I think there is vellum around it, and the vellum is very reactive to desorption or absorption of moisture, and that depends on the environment it is in. So the key is that not to be damaged, the material has to be in a state that basically is safely usable, right? So that can be the reading room. Now the question is, of course, what kind of difference do you have between storage and the reading room? And I believe really that the safe way to go is to minimize the change in moisture content between these two separate environments, and that way the access will be, and the use of the material will be safe. So how you can do that? Well, you certainly can do that, and we are trying to develop data not for vellum but for other hygroscopic materials. There is a combination of temperature and humidity that will give more or less the same moisture content in the material. So if you apply this kind of approach to the storage in such a way that there will be no difference at equilibrium between the reading room and the storage. Well, you don't have any more problem there because there will be no significant desorption or absorption, and the physical property should remain the same. So this is the idea that give me the opportunity to express it there.
I might just add that I think, Jean-Louis, correct me if I'm wrong, but I'm sort of based on your research of moisture equilibration. If there was a wait period, it might be a month or so for that entire volume, that entire book to equilibrate to the conditions of the reading room, which doesn't seem particularly practical. But as soon as you open the book, those leaves will respond.
Yeah, you're right. If you talk about the entire object, it's 3 or 4 weeks. Now, if the sensitive part, it's the cover, that is faster, as of course. So it's a little bit difficult to judge, you know, and what we talk about, if it's the entire object or the cover. But you're right, you can't wait for 1 month anyway, right? It defeats the purpose. So maybe the thing, the curator or the collection responsible should really observe what is really happening. In other words, they can do the same type of video, right? In a way, and look under which environment really this book can be handled without, you know, any damage or stress, etc., etc. I think there is a lot of knowledge out in the field there. That is invaluable, really, knowledge and information that could actually shape study that still need to be done, really.
I would add too, just like on a practical and this, you know, this volume that we've exposed to relative humidity, we didn't cause any additional damage to it for many reasons. One is being that the idea of proofing that it's probably already seen these highs and lows. And also, you know, if you kind of keep it within that 30 to 60 range, yes, the pages will respond, but response doesn't necessarily mean damage.
All right, we got time for a couple more questions, maybe one or two. One is I'll give it to the team again. What is the definition of short-term versus long-term fluctuations?
I didn't hear what you said.
What is the definition of short-term versus long-term fluctuations?
Okay. Well, that is it's a little bit maybe everybody has his own definition, but I think usually in the standards they give a recommendation based on daily change. That's mean 24 hours. And when we talk about long-term fluctuation, you know, think about seasonal changes, and this is over a period of months, really. That's my take on it.
Okay, and a follow-up to that came directly directed to you, Jean-Louis. It's which range of temperature difference within a storage space do you consider problematic?
Well, probably depend on material again. You know, if and the recommendation is, for example, for a lot of material, paper, film, and so forth, to use cold storage, right? And even frozen storage. So here you go from 70 Fahrenheit to 0 Fahrenheit. So it's a big gap. And then you also say that, well, you can retrieve the stuff. So you go from, again, 0 to 70 Fahrenheit. And with paper material, color photograph, and so forth, and film, it doesn't cause any problem. Not only studies have shown that, but use and application of those methods. So there is an uncertainty there now that when we look at temperature change, and we talk about that in the current study, temperature or heat or cool doesn't only raise and lower the temperature in a way, but has also the effect for hygroscopic material to promote either desorption or absorption of moisture, and that is linked to the physical property of the material. So the story may be a little bit more complex, as Kelly said, for some composite material there, and this is something we are currently looking into. That's been the magnitude of the change in moisture content. What still remains to do, it's what is the physical property changes of those material when you change the temperature and not necessarily change the relative humidity around it. And this is well, maybe this is good for the end of a session. It's a little bit an unknown answer to that question that I just mentioned here.
All right, I'll pass
Sorry,
it.
can I interject just briefly? I hope everyone can see I added to the chat box some references. The Canadian Conservation Institute's notes describe proofing further, and then the AIC Conservation Wiki, you can see a number of sources that are cited talking further about proofing. So I just wanted to show that they're there, and specifically there's a number of articles by Mecklenburg and Earhart, and you can see those listed there. They'll talk more about proofing.
All right, we're at a little after 3. Do you guys want to answer 1 or 2 more questions, or we can respond to everyone via email whose questions we haven't gotten to as well?
We can answer. That's fine.
Okay. Question for Al that came in: is there a good source for comparing strain rates in different materials?
Not that I know of. There is a group out of Poland that is working on a website that is looking at different materials, but I think they only have a couple of materials up right now, and I am having trouble remembering what that website is. But maybe, Chris, if you have that person's name or email, I can look it up and find it. But otherwise, not really. The group out of the Museum Conservation Institute under Mecklenburg did look at strain in materials that are all part of paintings. So they looked at if you're looking at a panel painting, they looked at the panel and they looked at the canvas, and then like the different layers, the gesso, and so on and so forth, mostly to determine where that sort of weakest point was. But otherwise, I haven't really found anything, but I will keep looking.
All right, we got another question I'll pass to Jean-Louis. Is there a difference between color film and black and white film about hygroscopic absorption?
Not, well, I could answer no, but I could also answer probably. The reason is all those film, even in the category color or black and white, the thickness of the emulsion can be different actually. And I was amazed a few years ago when, because basically this is a gelatin mostly in film who absorbs the moisture. The plastic itself, it can be acetate or nitrate, polyester absorb much less actually. But this is a gelatin will really make the difference. Typically the emulsion on a flat film is thicker right? And I remember years ago when I did a study on microfilm, and the idea was actually to find a way to condition material microfilm at a given level of moisture content. And so, well, microfilm is microfilm, but you know what? There is microfilm and microfilm. I was amazed as the difference in terms of moisture content, depending the type or even the manufacturer of the microfilm. So it's not that simple. Actually, there is little, but typically a film, it would be something like at normal condition between 2.5 and 3.5% weight of water. But if you compare with paper, paper might be 14% in the same condition. So there's quite a range between type of materials, which is even bigger. Okay.
All right, we'll take one last question and we'll call that it. Last question here is, has there been analysis between full or partially full enclosures and the rate of change for temperature or relative humidity?
Say it again? About the difference between enclosures?
Has there been analysis between full or partially full enclosures and the
yeah,
rate
okay.
of change for temperature or relative humidity?
Well, actually, that is an interesting question, because if you talk about film, or if you talk about full equilibration in terms of temperature, that will be dependent on two things. It will be dependent on the mass of material, definitely, because it need more energy to raise, of course, the temperature of a lot of materials than just a little bit, right? And actually, we see that in the current experiment, that the more stuff in a box you have, actually, the slower actually the temperature equilibration is. It doesn't mean that it will take days and weeks. No, it takes still hours, but you can see a difference in the shape there, right? And I would say the same thing in terms of moisture equilibration, because if you have a full, I don't know, a full box of photograph or full box of film or paper, to achieve this equilibrium, it will be either to absorb more water in the material or less water, depending if you go in the direction of desorbing or absorbing. So yes, it changes things. And the last thing I would say is, if you take material like film material, for example, and you look at the temperature inside the roll or the stack, the enclosure doesn't play any role actually. And that is because the film itself, it's really the insulating element there. So that is something also was interesting to see. So there is data out there, and we did publish some data about this. Were similar to those that Kelly showed during the webinar here. Okay.
All right, well, thank you, everyone, especially Jean-Louis and Al. Appreciate you joining us today. And said, please do complete the post-webinar survey and consider joining us for the next 2 webinars in the series. So thank you all and have a good day.
Ooh. Okay, that's it.
And hold on, I'm going to be ending this in just a minute.